ROC curves, or receiver operating characteristic curves, are kind of tricky. They're difficult to understand. So what we're going to do here is we're going to try to present them in as simplified a way as we possibly can. You may need to construct an ROC curve if you have a continuous variable that you're hoping to use to distinguish people who are ill from people who are well. If you do use a continuous variable, you have to have a cut point. In other words, a level above which you're going to say somebody is ill and below which you're going to say somebody is well. Now you have to figure out where that cut point is, and that's where the ROC curves come in. The way that you do that is, and this is going to sound very complicated, we're going to make it as simple as possible in just a little while. The way that you do that is you plot sensitivity versus 1 minus specificity across a range of possible cut points for that continuous variable. Now again, that sounds pretty complicated, but we'll make it as simple as possible. We'll start by considering the terms sensitivity and specificity. So many of you will remember that sensitivity basically refers to the ability of a test to find disease when disease is present, whereas specificity refers to the ability of a test to correctly identify people who are well. So what we're going to do first is we're going to replace the terms sensitivity and specificity with terms that I think are a little more congenial to being understood. So sensitivity we're going to change to true positive rate, okay? How often we find disease when it's actually present. We're going to change specificity to true negative rate. How often we correctly say that someone doesn't have disease. Now, in my opinion, this is still too complicated. I have a hard enough time just understanding true negative rate, and what 1 minus true negative rate means is the opposite of true negative rate. So whenever you subtract something from 1, in statistics speak, what you're doing is you're asking for the opposite. So let's go ahead and consider what the opposite of true negative rate is, and that way we can just use that directly instead of 1 minus true negative rate. So the opposite of true is false, and the opposite of negative is positive. So that means that instead of using this cumbersome notation 1 minus true negative rate, what we can do is just replace that with the false positive rate. So what we're doing is comparing the true positive rate versus the false positive rate across a potential range of values for a continuous variable. That's still kind of complicated. So let's see if we can make it still easier. Basically, we're just really considering positive test results. And you can, if you say somebody has disease, you can either be right or wrong. So let's just use those instead of true positive rate and false positive rate. So if you call somebody positive for disease, you might be right. In other words, they might really be ill, or you might be wrong. They, instead of being ill, they might actually be well. So that might be another way, or an easier way, to look at these portions or these labels for the X and Y axis. Okay. That still hasn't got us anywhere. We still have a ways to go. So let's look at some potential cut points and what might be good cut points and what might be bad cut points for telling whether somebody has disease or not. Let's look at how an ideal test would perform. And when I click here, an asterisk should come up right here, this green asterisk. This is how an ideal test would perform. In other words, every time you said somebody had disease, you would be right and you would never be wrong. So everybody that you said had disease would actually have disease. You would have nothing but true positives and no false positives. So all of your positive test results would be correct. Let's look at how the worst test in the world would perform. So this is what the worst test in the world would do. In other words, every time you say somebody has disease, you would be wrong. You would never be right, because the right here is 0 and wrong is corresponds to the number 1. Let's look at another couple of examples right here. We're going to look at all 4 sort of corners of the ROC curve. This is the next corner that we'll look at right here. This is what would happen if we called everybody who took the who had the test administered to them, if we called them all positive, no matter what value they had on the test. With this value right here, when we call everybody positive who has the test, we do identify everybody who has disease. So our sensitivity is going to be 100%. unfortunately, all those people who are well, we're going to misidentify them as having disease. So our sensitivity is 100%, but our specificity is 0%. Remember, we're saying 1 minus specificity right here, which is why this is a little bit tricky. But basically, we're calling everybody who has disease, or we're correctly identifying everybody who has disease, but we're also identifying a lot of people who don't have disease as being ill. Let's come down here and look at this corner right here. At this point, what you're doing, instead of calling everybody positive like you did up here, you're calling everybody negative. Well, that's really good in terms of the people who are healthy. You're never going to be wrong in terms of somebody being well, or you're never going to misidentify somebody that is actually well as being ill if you call everybody negative. But of course, your sensitivity is 0, and there's no point in doing a diagnostic test with a sensitivity of 0. So those are sort of the parameters for looking at the ROC curves. I'm sure it's still kind of complicated and mysterious, so we're going to go over an actual example next. This is a normal, healthy appendix, and this is a diseased appendix. And I hope you can see, despite the fact that there's some differences in magnification here, that the diseased appendix is filled with debris, and the reason it's filled with debris is that it's obstructed. The pathophysiology of appendicitis is that the appendix gets obstructed with typically an appendicolith, and all those cells inside the appendix that are producing mucus, well, by golly, they just keep producing mucus. And eventually what happens is that the appendix becomes really dilated, and if it becomes dilated enough, what happens is that you get a venous infarction, and that will lead to overgrowth of bacteria and subsequently appendicitis. Now, it stands to reason then that you could use the diameter of the appendix to decide whether or not somebody has appendicitis. That's what we're going to do. Our continuous variable for this example right here is going to be the diameter of the appendix. And there's going to be some diameters, or we're hoping that there's one diameter that's a good cut point that accurately discriminates between people who do and do not have appendicitis. So let's go ahead and work through an actual example. So here's some data right here giving you the sensitivity and specificity for predicting appendicitis based on the diameter of the appendix. Now, this information right here came from my favorite place. I made it up. So this is not real data. This is made up data. Okay, so what I've said here is that if you have an appendix if you use 1 millimeter of dilatation of the appendix is deciding whether or not somebody has appendicitis, that you have a sensitivity of 1 and you have a specificity of 0. And if you have a diameter of the appendix of 25 millimeters, that your sensitivity is 0 and your specificity is 1. And let me go ahead and explain why I've decided to set these numbers up the way that I did. Basically, if you use 1 millimeter of diameter of the appendix as your cut point for deciding whether or not somebody has appendicitis, you're basically going to call every single person who has an appendix positive for appendicitis. So remember, when we called everybody positive, this is the equivalent thereof. So anybody in whom you identify an appendix, potentially you could use that to decide or to say somebody has appendicitis. So that would give you a sensitivity of 100% because you'd be calling everybody positive, but your specificity would be 0% because you're incorrectly labeling everybody who's well as having appendicitis. Let's go back and look at this number right here. Let's say you waited until the appendix was 25 millimeters in diameter before you called somebody positive for appendicitis. I don't think that an appendix can make it to 25 millimeters without bursting. So basically, if you're going to wait for the appendix to get to be 25 millimeters in diameter, you're never going to call anybody positive. This is obviously terrible for sensitivity since you're never going to call anybody positive, but it's great for specificity. Basically, you're operating down here where you're calling everybody negative. So sensitivity is going to be awful, but specificity is going to be fantastic. And then these other levels or these other potential cutoffs sort of fall in between these two extremes. Now remember, when we plot sensitivity versus when we make our plot here, we don't plot sensitivity versus specificity. We plot sensitivity versus 1 minus specificity. So I've put that right here. So let's go ahead and plot some of these numbers. We'll start with this cutoff right here, where we've used the cutoff of 1 millimeter to say 1 millimeter diameter appendix to say somebody has appendicitis. Well, what we're doing then is we're saying that everybody whose appendix measures 1 millimeter or larger in diameter has appendicitis. So basically what we're saying is that everybody who has an appendix has appendicitis. Again, great for sensitivity, 100%, but we're basically labeling everybody who does not have appendicitis as having appendicitis. So we get everybody who actually is well wrong. So we're going to end up here, and that's not where we want our cutoff to be. Let's look at another cutoff. We're going to look at this one right here, where we've decided to put 20 or use 25 as our cutoff. Remember, no appendix is going to make it to 25 millimeters, at least in my made-up world. So basically, in that case, our sensitivity is going to be 0 because you're never calling anybody positive for appendicitis, but you have great specificity. Your specificity is going to be 100%. And these other numbers are going to fall along here and make this nice curve where you can potentially find a cutoff. And the cutoff that you're going to choose usually is the one that's closest to this ideal value. Again, all these numbers that I've used right here, I made them up. So don't use them in real life. Don't go to the abdominal imagers and tell them that Dr. Tig has told you that these are the correct numbers, because they're not. We're just doing this for the sake of this ROC curve. And we can go ahead and plot the ROC curve out like that. Anyway, that's how it works when you use an ROC curve. You can even use ROC curves to compare different diagnostic tests. Let's say you wanted to compare CT versus ultrasound. What you would do is plot ROC curves for CT and ultrasound, and you would calculate which diagnostic test had a greater area under the curve, and that's the one that you would tend to use usually. Thank you for your attention.